Hey, welcome back. So I wasn't planning to make another video about this lathe so soon, but unfortunately there have been some unforeseen catastrophes, and I figured I might as well make a video out of it. So this is going to be a bit of a shop talk video, but we're also going to do some machining, because I'm going to show you how I'm replacing the proprietary and very dead electronics inside my lathe with a completely new and custom motor and VFD solution. So a few weeks ago when I came into the shop and tried to turn on the lathe, it immediately flipped the breaker, which is never a good sign. And pretty soon it became clear that I wasn't going to get any work done that day, because it turns out this driver board for the motor that sits in the back here was completely blown. For the most part, this thing contains a VFD or variable frequency drive, and just to warn you, I'm going to be saying VFD a lot in this video, so there's your opportunity for a very bizarre drinking game. So this board drives the motor of the lathe, and that's what allows you to adjust the speed, and it's also what all the controls connect to, and unfortunately it's also the weak point in this type of machine, because these contain a lot of complex electronics and they're somewhat notorious for dying unexpectedly, and it's very difficult to fix them unless you have some advanced knowledge in this field, which I don't. And on top of that, they're usually proprietary and unique to each machine, so it's not easy to replace them either. I've actually had a friend who's an electrical engineer take a look at this, and it turned out that 3 of these IGBTs here had blown up or shorted, so I actually ordered replacements for those and switched them out, which did work at first in the sense that the lathe didn't flip the breaker anymore, and I could actually turn it on and see the display light up. But as soon as I started the motor, the board noped out again with a little smoke cloud, which means there's most likely other damaged components on there, and from what I understand, figuring all of that out and repairing it takes a lot of time and turns into a game of trial and error, so the board is toast, and that only really left 2 options for me. Option 1 is to get a replacement for this board, so I asked the place that sold me this lathe, and they quoted me a price of almost 400 euros for this thing, which I think is ridiculous. But unfortunately I wasn't able to find them for cheaper even on AliExpress. I'm absolutely not willing to spend 400 bucks on something that I know has a very high likelihood of just blowing up on me again in a few years. So I decided to go with option B, which is to completely get rid of this thing and install a much cheaper non-proprietary VFD that essentially does the same thing and even comes with a few extra advantages. So this is the one I'm going to use. This is a bit on the cheaper side. It's a Saco SKI-780, and you can find these for around 100 bucks online, but there is a caveat here because I can actually use this with the existing motor. So one reason the original VFD is so expensive is because this motor and VFD combo is a bit uncommon. This is actually a 3-phase brushless DC motor, and besides the usual cables you find on a 3-phase motor, it also has a whole bunch of these little ones, and these are sensor cables that the VFD uses to get feedback from the motor. So it's basically a closed loop system, which from what I understand offers better performance. But as with most of this stuff, I can't go super into detail. The bottom line here is the motor only works with a special type of VFD, and that VFD just blew up on me, so this unfortunately will just be a fancy paperweight for now. The new VFD on the other hand is designed to work with any standard 3-phase asynchronous motor, which is great because these are extremely common and that also makes them cheap. So even though I bought a brand new motor for the lathe, I'm still saving about 150 bucks with this setup compared to replacing the original board. And if anything ever does break again, it'll also be much easier and cheaper to fix it in the future. So after that long-winded introduction, let's start with something practical, because this conversion turned out to be a lot more involved than I first thought and also requires building some things. The new motor happens to fit into the hole in the back here so perfectly that it makes me think the lathe was originally designed with one of these in mind, but it will require some custom mounting solution because the original motor was attached to the casting of the lathe using this bracket here, and since the motors have a very different form factor, it doesn't fit the new one at all. So I checked what materials I have in the shop, and I found this steel plate and some flat bar that looks pretty suitable for building a beefy bracket. Nowadays I like to build a quick 3D model in Fusion even for small stuff like this, because it doesn't take me much longer than drawing a sketch on paper, but it's a lot more accurate and saves me a lot of time in the actual build. That being said, the way my computer workstation is set up in the shop right now is, to be honest, kind of a joke, which brings me to today's sponsor, because FlexiSpot offered to send over one of their height adjustable desks, which I think is going to be a very useful addition to the shop since I do more and more computer work in here now. It came super well packaged and was very easy to set up thanks to a proper manual, and the first thing I noticed is just how heavy these parts are, which is definitely a good sign for a desk frame. Everything is made from steel with very little plastic being used. The fit and finish is great and even the welds look solid, so I can see why they give you a 10 years warranty on these. The range of adjustment on this goes from children's table all the way up to comically tall. I'm 6'4" or 194 centimeters tall, and if I put this all the way up, it's too high for me to use. So I think it should fit pretty much anybody. This model is the E7 Pro, and FlexiSpot says it can lift up to 440 pounds, which I haven't tried yet, but I weigh about half that and it had no problem lifting me at all. So even if your keyboard and screens are made of lead, this shouldn't give you any problems. The desk also comes with a cable tray underneath, so you can get a nice clean looking setup like this. So far I've never really felt that much of a need for a standing desk, but I have to admit here in the shop it actually makes a lot of sense to switch between standing for smaller tasks and sitting down for longer screen sessions. So I'm starting to see why many consider this a must-have feature for a desk. A lot of you have probably also seen my desk build videos, so you know I'm a bit of a desk nerd. And of course that means this here is not the final setup. I'm planning to do a whole build around this desk to turn it into kind of a custom workstation for a whole bunch of stuff in the shop. So you can look forward to seeing that soon. But for now, let's continue with the video. And if you're interested in getting a standing desk, you can find a link in the description. I'm cutting the flat bar to length now, and I can even cut the plate using the bandsaw using some workarounds. It does bottom out halfway through, but you can get around that by just flipping the plate. And at the bottom I have another plate to stabilize it to avoid vibration. And I also put a piece of thick filler rod at the top of the vice jaws, which ensures proper contact on the top and bottom. I then cleaned up the saw cuts and brought the plate to final dimension on the mill. I know it's overkill, but I also know you guys love watching overkill. Next it gets some mounting holes, and I marked the center of the cutout for the motor here to make it easy to scribe a line around the outside, because I'm going to shape that on the grinder later. Then I used a big hole saw to prepare the cutout, but it's a bit too small, so I'm going to finalize that with a boring head. I drilled the hole circle here using the circle function on the DRO, and as usual I made twice as many holes as I need because it doesn't take that much longer and allows for more possible mounting positions. I'm not sure if I showed this tool before. This is a little air-powered chamfer mill, and this thing is awesome for deburring and chamfering features like this big cutout. Then it was time to cut off the edges and shape the outside radius. Technically this could have just stayed a rectangle, but as you know I like to take a few extra minutes to make things look nice. After some more chamfering, this part is now done, so I'll prepare the two pieces of flat bar next. In this case, milling the parts is actually somewhat necessary, because this is also the reason I'm not welding these parts. The connection between this and the plate also determines the alignment of the motor shaft to its counterparts. And machining things is just a lot more accurate than welding if you want things to end up at a right angle, but making this a screwed connection also gives me an additional benefit that you're going to see in a bit. So here's the finished bracket, and this is what I meant by keeping things square. It also fits nicely on the new motor, so let's try installing it. I probably don't need to mention that it's an absolute pain to work inside this casing here, because the only way to reach things is through the side, which is blocked by the bracket, or from the top. And I could have made this a bit easier by moving the lathe, but I really didn't want to do that because I leveled it with the machine water level, and if I move it I have to repeat that tedious process. Here's what I meant by it being an advantage to screw the plate on, because I couldn't have installed those screws inside the case with the motor also in there, or at least it would have been a lot more tricky. So now I can simply unscrew the front plate and attach that to the motor and put them both back as one piece. So far this is looking great. I just need to make one small adjustment now, which is to enlarge the hole in the pulley, because the shaft on the motor is slightly bigger in diameter. And this would be a super simple job if I had a working lathe. But since that isn't the case, I put this on the mill where I had to indicate it manually. And I know this is not an ideal way to hold a round part in the vise, but I only need to remove a tiny bit of material, so it worked out fine. Now that the motor is installed, let's deal with the new VFD. I was originally going to mount this to the wall outside in an electrical cabinet, just like I did with the belt grinder, but eventually I figured it would be a lot more elegant to have this contained inside the lathe like the previous one, because it's fairly compact, so it does happen to easily fit into the same space. So I came up with this slightly unusual way to mount this. There's this steel bracket in here that the control board was attached to, and it's pretty sturdy, but I don't want to screw on the new VFD because I might have to pull it out of there now and then. So I designed and printed this big bracket thing, which has a slot built in so that it can slide over the steel bracket, and the VFD neatly nests on the inside without blocking any of the vents. So it kind of floats inside the casing, which might also reduce the vibration a little bit, and it's easy to access when I need to, and thanks to being angled forwards a bit, I can also read the display and reach all the buttons to program it. Once all the external controls are set up, I won't actually need the buttons, so then it can just disappear, and the lathe is pretty much going to look like it did before. And one further advantage of this solution is that I can reuse a bunch of the wiring that's already inside the lathe, because the emergency stop and safety switches will actually cut power to the VFD the way this is connected. Same goes for the main power switch, which I can flip on now to power the VFD up, and the next step is to set up a whole bunch of parameters. I'm not gonna go super into detail on how to configure one of these things, because there's already dedicated videos for that on YouTube that explain it very well. But to give you the basics, the most important thing you need to do on almost all of these is to set up the motor parameters, which mostly consists of copying the data you find on the specification plate of your motor. So in the manual it tells you all these function codes and what they do. So for example, if I want to set the motor power, I can access the P1 menu and then change the first parameter, which is set to 0.4 by default. And since I'm using a 1.5 kilowatt motor, I'll set this to 1.5 and save, and then you kind of keep going like that. So for example, P105 is the parameter for the motor speed, so I'm changing that to the rated RPMs of the motor. These VFDs have an insane amount of settings, so well over 90% of the parameters in the manual will be irrelevant to most people, but setting up the motor parameters is the very least you should do to ensure the motor runs correctly and you're not damaging it or the VFD. Now that everything is set up, I'm also going to connect the two. And again, there's lots of videos about this stuff specifically, and it also depends on what kind of motor and power input you're using. So I'm just showing you the general steps here so you have an idea how the overall process works. The other end of this cable now gets connected to the VFD, and this one is a single-phase VFD that can actually generate 3-phase power from a single-phase input, which is another reason a lot of people use these for various machines. Now with this connected, we can give the motor a spin, and it looks like it works fine, so I can reinstall the belt tensioner and the drive belt. And with that, I technically now have a running lathe again, which is quite a relief. But of course we're not nearly done with this. Currently the VFD can only be controlled using its own control panel, which of course would be very inconvenient for using the lathe. So next I'm going to set it up for external controls, which means once again ripping apart this control panel, which I have only recently updated. So first I'm desoldering all the switches that I used to bypass the original controls on this board here. This thing connects to the broken driver board, so it's of no use to me at this point. Unfortunately, I also have to get rid of most of the switches I installed last time, and this is because the new VFD wants different inputs. For the speed there will be a potentiometer instead of the digital input before, and for starting and stopping the spindle, the old VFD wanted push button signals, while the new one wants a switching signal. Meaning I need something more like this on-off switch, where there's two positions for forward and reverse, and when it's turned off that means stop. I'm not actually going to use this switch though, because I feel like it would be too easy with this one to accidentally flip it in reverse instead of stopping it. But I happened to find this huge switch in a box, which actually used to be the main power switch for this lathe. And this is two very definitive positions, and it really has a nice chunky feel to it. So I think this will be perfect as a new start-stop switch. Next I'm running some new cables in there, including the one for this thing, which I'm going to explain more about in a second. And now I once again need to make modifications to this plate here. First it gets some additional clearance for the potentiometer, and then some screw holes for the new switch. Since the RPM display was part of the old VFD, I'm also installing a new standalone speed sensor, so I printed this little bracket for the display, which will also get screwed onto this plate from the back. So this thing I showed you is the Hall sensor for measuring the spindle speed. Luckily this fits inside the casting here, directly where the spindle is, so it'll be invisible later. I made this little bracket for it by just bending some flat bar on the vise, and that gets installed now, and the counterpart for this is a little magnet. I'm just sticking this onto the spindle using some super glue, and I installed the same thing on my mill, so I know this is sufficient to hold it in place even at high RPMs. It's pretty important to set the distance between the sensor and the magnet correctly for these to work. So there should only be a tiny gap, and now every time this magnet comes around, the sensor sends a signal to the display, which then tells you the speed more or less accurately. To this day I've only found one type of these RPM displays online. They're all over eBay and similar sites. They're very cheap, and having installed one on my mill before, I can confidently say they're absolute trash. They don't come with any kind of manual, so you have to kind of guess yourself through the wiring process using the very sparse information on the mostly Chinese label in the back. And they're also extremely susceptible for electric interference, so even though it does the job, I kind of hate having to use this thing. So if anyone knows of a better product that's more or less plug and play, feel free to let me know. Another thing I did to finalize the wiring was to exchange all of the screwed wire connectors with these Vago clamps. I don't know how common these are outside of Germany, but they're incredibly convenient, and as far as I know also safer than screw clamps. You simply stick your cables in and snap them shut and you're done, and they also make it very easy to change things later. So next let's connect all those control wires to the VFD. Again, this probably looks more complicated than it is if you've never done it. We only need the upper row of this terminal. So from left to right, we have a 10 volt output that's going to be connected to the potentiometer, as well as the AL1 input, which is the analog input for the speed. Then we have the ground, which is already connected. And on the right of that, we got DI1 through DI5. And these are all digital inputs you can program yourself. So basically when we connect DI1 to ground, for example by using a switch, the VFD gets a signal and you can choose a whole bunch of stuff from a list that you want it to do when that happens. In this case I'm just going to use DI1 and DI2, so I'll connect those to my switches and set those commands up for forward and reverse, and that's pretty much all I gotta do to run the lathe from the external control panel. The panel looks a bit messed up right now, but I'm gonna repaint that in a second. For now I'm just gonna install the various controls and the display to see if everything works. The controls seem to work, and the display is also getting a signal from the sensor, so that's good. In case you're wondering, yes, the display really has a refresh rate of like 4 seconds. It's more for minor annoyance and not really a big deal when you actually use the machine. But besides the fact that it feels like it has the build quality of something you'd expect to find in a vending machine, and sometimes shows gibberish for a few seconds when there's a load spike, that's what I mean when I say these things are trash. It does do the job, but if I could buy something that's twice as good for twice the money, I would never buy one of these again. You probably noticed I ended up with a few empty holes here because the new controls are a bit simpler, so I figured I'm just gonna use this one for a power indicator, because it can't hurt to have one besides the display. So I just turned this little part from white POM and stuck an LED in there, which connects to the 10 volt output of the VFD. And for the larger hole I just made this simple plug for now, but maybe I'll think of something functional to put there as well at some point. For this spindle control I'm of course not going to use that ugly red knob, so I'm making a fancy one that matches the other handles on the lathe. And this was also a good opportunity to give the new motor a try, which so far is performing pretty much like before. With that I can finally screw this back on, and of course I also made some labels, so another iteration of this panel is now finished. And I gotta say, I actually like this even better than before, because the controls are actually more intuitive this way, and the chunky switch is just very satisfying to use. So now it's down to just making a few little adjustments to the VFD settings, which is one of the advantages this solution gives me over the proprietary VFD. Let's just start the motor for a second and let it spin up to full speed and then stop it. You might have noticed this takes quite some time, but the cool thing about VFDs is you can actually set how fast this accelerates and decelerates. So on this unit it's set to 10 seconds each by default, so I'm gonna halve that and see what happens. As expected, it speeds up and slows down quite a bit faster, but I should mention that the power braking puts some serious strain on the VFD internals, because it turns the motor into a generator and the energy from all that momentum has to be absorbed somehow. In theory, the VFD has protection systems in place to prevent overvoltage and overcurrent, in which case it should turn off the electric brake, but I wouldn't necessarily count on those. And if you wanted to slow down even faster, there's actually a solution. Not all VFDs support this feature, but this one has a dedicated connection for a brake resistor. This thing is probably not what most people expect when they hear resistor, but that's what it is, just much bigger than you normally see. It wasn't super expensive either. I paid about 20 bucks for this. And the specifications for it depend on your VFD model, but basically with this connected, the extra energy from stopping all that momentum should get dumped into this resistor and turned into heat, which protects the VFD and lets you use more aggressive brake settings. Now with the resistor connected, I set the brake to 2 seconds, which is as low as I dare to go, so let's give that a try. The machine now slows down about 3 times faster than it did in stock condition, and if you brake from a slower speed it's even faster, so under 500 RPM it's almost instant, which is a huge time saver for those operations where you need to start and stop the spindle a lot. I also wanted to see if it still works with more momentum, so I put a chunky piece of stock in the chuck, but it seems not to affect the braking at all. The resistor now gets permanently installed in the casing here, and I can already hear people say everything is gonna overheat in there, but I seriously doubt it, because unlike the old ones, the new VFD and motor both have active cooling fans, and there's also quite a bit of room in the case, and it has a lot of vent slots and holes everywhere, so I'm not worried about sealing it in its little sarcophagus now. There's one last thing I want to do now, and that is to make a smaller drive pulley. What this is going to do is allow the lathe to have considerably more torque at the low end, which is usually the bottleneck with the VFD setups. although I can't say it's ever been an issue for me, and the newer VFD does even have a torque boost setting. But with the new setup I can actually get this benefit without losing my top speed, and I'm gonna explain how that works in a bit, but first let's make that pulley. To start the V-groove I just plunged in there with a parting blade to get things started, and then I had to get out the old compound slide to make the tapered features. I actually used the parting blade to cut the tapers as well, because I don't really have another tool that fits in there, and luckily on aluminum you can get away with this sort of thing, because I'm pretty sure this would shatter like hell if it was steel. And in case you're wondering, you can of course buy these pulleys and they're not that expensive. I actually had ordered one, but then it was out of stock and I got impatient, and also I've never made one of these before, so it's good practice. After broaching the keyway, the new pulley is now done, so here it is compared to the old one. It's about 40% smaller and came out quite nice, so let's install that and give it a spin. So of course I'm getting lower RPMs now. The spindle goes up to around 1200 with the new pulley, which by the way is still faster than I run the lathe most of the time. But like I mentioned, we can actually improve that now, because another cool thing about VFDs is that they actually allow you to overclock motors as well. So the VFD can not only change the electrical frequency between 0 and the 50 Hz the motor is rated for, you can actually go way beyond. In fact, up to 400 Hz, which I'm definitely not going to try, but let's try setting it to 60 for starters. At 60 Hz I'm now getting around 1400 RPMs, but we can still go higher. From what I've read, you can run most 3-phase motors safely up to about 80 Hz, and probably even higher, but it makes sense to increase it incrementally and watch how it behaves. So I took off the belt here just to have the motor run on its own, and it seems like it's running nice and smooth. If you go higher than the rated frequency, the torque will start to drop off at some point, but I'm not concerned about that, because when you're running the lathe fast, it usually means you're working on a tiny part or with a tiny tool, or you're working with materials like plastics or soft metals. In all of those cases, the cutting forces will be quite low, so you don't really need much torque at the high end. I almost never run the lathe this fast anyway, so I don't technically need to overclock it. But I figured it can't hurt to have the option, and I wanted to show you it's possible. So I'm now getting 1900 RPM max, which is pretty much what the stock version runs at. So this concludes the third video I've done on this lathe, and as glad as I am to have it running again, I hope it's the last one for a while, because at this point this is most likely the least stock version of this particular model in existence. If you have any questions, drop them in the comments, and as always, thanks for watching.